In this lesson, we're going to learn about collision theory. So there are 5 different factors that affect the rate of a reaction, or how fast a reaction is occurring. So there's temperature. The hotter that reactant molecules are, the faster they're moving, so the greater kinetic energy they have. Concentration, so a higher concentration means we have more molecules in a given space. Surface area, so the larger the surface area, the more molecules there are that are available to react at any given point. The nature of the reactant, so we're going to talk about this one in more detail. And catalysts, so things that are added into a reaction, they're still there at the end, but they change throughout the process to allow for reactants to come together and form products quicker, and then they are back to the same substance they were at the beginning. So they don't get used up in a reaction, but just allow a reaction to occur faster. And then things that we can do to mimic the different reactant molecules colliding faster are to shake or stir the system. So any type of agitation that allows those molecules to collide with each other faster. So according to collision theory, a chemical reaction is going to occur when reacting particles collide with one another. Now, not all collisions are going to result in a chemical reaction. Only a small fraction of collisions will actually result in a chemical reaction. And that fraction can change as we change temperature and concentration and things like that. So there's certain criteria that has to be met. So for a collision between reactant particles to be effective and to create products, the orientation of the reactants is important. So the actual collision geometry has to be favorable. So they have to collide in a way that those bonds would actually end up breaking in the reactant molecules and forming for the product molecules. And there also has to be enough energy of the collision for products to be formed. So the first criteria was correct orientation of reactants. So what does that mean? If we take an example here of nitrogen monoxide and nitrogen trioxide reacting to form 2 nitrogen dioxide. So if we take a look, we have oxygen is red, nitrogen is blue. So I have nitrogen monoxide and nitrogen trioxide. So what is important to look at to see if a certain orientation of the 2 molecules in relation to each other would produce a reaction, what we need to know is what NO2 looks like. And so NO2 is a nitrogen with 2 oxygens attached to it, and you can see that it has this bent shape, similar to water. It's not the exact same as water, but we have a similar idea here as water. So it's not a linear. So what I need to happen then is for the nitrogen monoxide to be in relation to one of the oxygens from nitrogen trioxide. The nitrogen from the nitrogen monoxide needs to be colliding with one of the oxygens because that is where the bond is going to form. And we need the correct angle as well. So in this case, we have the nitrogen and an oxygen colliding. And we also, oh no, not here because not from that one. So we have the correct atoms are coming towards each other, but this doesn't create the right shape for nitrogen dioxide. So this angle specifically, which is the same angle that we see in nitrogen dioxide. So where the bonds are going to form, we need those 2 atoms to collide, and we also need the angle that it comes in at to be the same angle as what it would be in the product molecule. So this is the only other one where we have the correct atoms colliding. So the nitrogen from nitrogen monoxide with one of the oxygens from nitrogen trioxide, but there's no reaction here. So this collision is not effective because we don't have the correct angle. So we need not just the correct atoms, but also the correct angle. So over here, we don't have the correct atoms. We have 2 oxygens, but it's not 2 oxygens that will be bonded to one another. Here we have the oxygen from the nitrogen monoxide, and that is going to need another oxygen on the nitrogen. So this is going to produce no reaction. And here it looks like the nitrogen is coming in and hitting the other nitrogen there. And even if it ended up colliding with an oxygen, it's not at the right angle there. So over here we have both the correct atoms, nitrogen from here and one of the oxygens, and also the correct shape for the nitrogen dioxide. So the first criteria is correct orientation, which means the right atoms and the right angle for the collision. The second one was just that there is enough energy. So if 2 molecules just kind of pass by each other and barely end up touching one another, or if they collide and it's just not enough energy, then there will be no products created there. So the activation energy, which is represented by the symbol capital E with the subscript A. So activation energy is the minimum amount of collision energy that is required for a chemical reaction to occur. So on this graph here, we have a lot of collisions happening here. This is the amount of energy that they are colliding with, and this is how many. So we have some collisions that are happening at a low energy. As the energy increases, we have more and more collisions, and then we're starting to have less collisions that have this amount of energy, and then we hit this point. And any of the collisions that collide with at least this amount of energy will produce a reaction. So we can see that it's only this part of the graph where collisions will produce a reaction. So all of these collisions, the reactants are going to stay as reactants. They are not going to produce any product. So the collision energy depends on the kinetic energy of the colliding particles. So the hotter that the temperature is, the more kinetic energy that particles have. And the higher their kinetic energy, the more effective collisions are likely. So the more energy they're colliding with. So how can we, on a graph, show a chemical reaction? So from left to right on what we call a potential energy curve, we can look at the potential energy increases as a reactant becomes closer. When the collision energy is greater than or equal to the maximum potential energy, reactants are going to transform to what's called a transition state. So we'll take a look at what that looks like in a moment. And in that case, products are going to form, or sometimes reactants can reform if it is ineffective. So if we take a look here, we have talked before in energy, we have talked about the energy involved in reactants and the energy involved in products, and we looked at the difference between those two, which was the delta H. So the additional part we're going to look at is that not all collisions will result in products being formed. And so we have, this shows the activation energy. So we need more energy than what the reactants and products have for a collision to result in products being formed. So in these energy graphs, we are also including the activation energy, and this amount depends on the temperature. It is not related at all to the delta H. How much the activation energy is has nothing to do with the delta H. So up here is the section that we call the transition state. And so this is going to be neither a reactant nor a product, but we're going to get this complex in between reactants and products where the bonds between reactants are starting to break, and at the same time the bonds between the products are starting to form. And that happens at the very top of this curve, And that point is called the transition state. So that's where the transitioning between reactants and products starts to happen. So this is for an exothermic graph. So we have a delta H, which is negative in this case. So our products have less energy than the reactants. So where did that energy go? That energy went into the surroundings. So that is exothermic. Here, if our reactants have a lower energy than the products, then the reactants are going to require energy from the surroundings. And so that is an endothermic reaction. We still have a transition state, which is higher in energy than either the reactants or the products. And so in this case, the activation energy is from the energy level of the reactants all the way up to the transition state. So this is also from reactants up to the transition state, but it's only a little bit above reactants because reactants are above products. Whereas here we have from down here all the way up to the transition state. And in this case, the delta H is the difference between the products and the reactants. So here also between products and reactants, the difference is that the activation energy here is the delta H plus the difference between products and the transition state, Whereas here we have the activation energy is just this top section and the delta H is this section. So either way, the activation energy is the difference in the energy of the reactants and the energy at the transition state. So reactants and then transition state. And the delta H is just the difference between the energy of reactants and products. So difference in energy between reactants and products there. So that one was exothermic and this one was endothermic. So the activation energy for a reaction can't be predicted from delta H. So the delta H value has nothing to do with the amount of energy required for the activation energy. The delta H is only the difference in potential energy of reactants and products. The activation energy we can determine by looking at rates of reaction at different temperatures. So the activation energy can be different at different temperatures. So reactions that have a low activation energy occur quickly because we are going to have more collisions that have enough energy when they collide for a reaction to occur. And reactions with a very high activation energy means that a lot of the collisions that occur won't be occurring with enough energy. And so in that case, we are going to have a very slow rate of reaction. So this shows a potential energy diagram for the combustion of octane. So we have our reactants over here, the activation energy, so the transition state would be up here. And our products have less energy than our reactants. So that means the delta H is going to be negative, which means that energy is given to the surroundings. And so this is exothermic. Okay, looking at reversible reactions. So when we look at a potential energy diagram, we can look at both the forward and reverse reaction. So if we go from left to right, that is the forward reaction. If we go from right to left, that's going to be the reverse reaction. So if I look here, carbon monoxide and NO2 combine to form carbon dioxide and nitrogen monoxide. And the delta H for that is negative 226.1 kilojoules. The reverse reaction would start with what are the products in the forward, so carbon dioxide and nitrogen monoxide, and produce what were the reactants for the forward, so carbon monoxide and nitrogen dioxide. And the delta H for that would be equal in value but opposite in sign. So this would be an endothermic reaction requiring 226.1 kilojoules. So if we take a look at this, carbon monoxide and nitrogen dioxide our reactants. Here's a small activation energy, so this is of the forward reaction. And then we have our products. So the delta H is just the difference between reactant and products. And when going from reactants to products, that's a negative. So that is an exothermic reaction. If we move in the opposite direction, so for a reverse reaction, we would start here and move like this. So here, our activation energy for the reverse reaction is from here all the way up to here. So this is our activation energy of the reverse reaction. Our delta H is still the same because it's just the difference between reactants and products, although this time we are starting here and moving up. So in this case, our delta H is positive, but the value is the same. So what we can see is the activation energy for the reverse reaction is equal to the delta H plus the activation energy for the forward reaction. Or another way of stating that would be that, the delta H is equal to the forward reaction, so coming up here, and then subtracting the activation energy for the reverse. And that will leave me with the delta H for the reaction. Okay, so if we are looking at potential energy diagrams, we have here methyl bromide and hydroxide, and those are reacting to form methanol and a bromine ion. So if we take a look here, we have our reactants over here. So we have a certain amount of kinetic energy, and as collisions are occurring, any collisions that occur with at least this amount of energy can result in our products being formed. So here at the transition state, we have what is called the activated complex. So a hydroxide is going to come in and collide with, and remember we have to have correct geometry. So the carbon atom is what the hydroxide will be connected to. Right now we have a bromine atom connected to that. So a hydroxide needs to come in and collide with the carbon with the right geometry. And so what we can see here is at the same time, the bond between carbon and bromine is starting to break. And we show that with this broken line or dashes or dots. And the hydroxide and the carbon are starting to form a bond. So this is called the activated complex that happens at the transition state. So we have partial bonds, the partial bonds that were part of the reactants and the partial bonds that will be part of the product. So we don't have, these are not proper bonds. So these ones are starting to break while these ones are starting to form. So we're somewhere in between reactants and products at this point. And then as that completes, now we have methanol and a bromine ion.